I want to start today with a question. So let's say I want to go to Iowa City. Now, for those of you who don't know, Iowa City is about 60 miles due west of my position right now in Bettendorf. We travel basically straight west on Interstate 80. It takes about an hour to get to Iowa City. So if Iowa City is 60 miles due west, and it takes me about an hour, how fast am I going? Think about that a second. How many got 60 miles an hour? Yeah, it kind of makes sense. I mean, I was going 60 miles. It took me 1 hour. We call that 60 miles an hour. But was I really? Because I got to think that coming out of my neighborhood, if I was going 60 miles an hour in my neighborhood, my neighbors would be pretty mad. If I was going 60 miles an hour on Interstate 80, the guy behind me is going to be pretty mad. If I look down at my speedometer, on Interstate 80, I'm probably going more like 70. Where exactly am I going 60 miles an hour? Well, 60 miles an hour is where I'm going as I'm accelerating up to 70 on the interstate. So what is 60 miles an hour? I went 60 miles. It took me 1 hour. I went 60 miles an hour. This is actually called my average speed, or in physics we call it our average velocity, which we're going to learn about. We have both instantaneous velocities. That's what I'm going right now. That's what's happening on my speedometer. We have an average velocity, where we look at the total distance and the total time. We have an initial velocity, where the velocity that I started. I have a final velocity. We have all kinds of different ways in which we can describe just one variable. Let's see if we can't figure out more about this. All right, let's talk a little bit about graphing and how that car moved and what data the car or the Tesla car actually gets from those sensors. As the car's moving away, let's talk about that. You're moving away from what we would call the origin. What did that graph look like? Well, if we look at some axes here, we would say that this axis over here was position, and that position is measured in meters. This axis down here is called time, and that's in seconds. So these are our axes for our graph. Now, if the car started at the origin, we would maybe put our first dot right here, right? If it didn't start at the origin, at time 0, we could put our dot anywhere up here. It, of course, didn't start exactly at 0, so let's put it a little bit higher. Then, over time, the car started to get farther and farther away. Maybe it was 1 meter, 2 meters, 3 meters, 4 meters. So over time, 1, 2, 3 seconds, it starts to get farther away from the origin. What about when it was moving faster? Can you tell me what a graph would look like if you're moving away from the detector and moving faster? Well, if we did that, it might look something like this. This graph here, if you'll notice, in the same amount of time, let's call it 2 seconds, the first car, which we would call slow, only went less than 3 meters. The second car, which we would call fast, went actually in 2 seconds. It went over 3 meters, almost 3.5, starting from the same origin. So these two graphs actually show us the speed of the car. What's different about these graphs? What's something that these graphs, in math class, what would you say is different in these graphs? We would say that they're both linear, but one of them rises a little quicker than the other. What's that called when you rise over your how far that the graph is actually run? Well, in math, we call that the slope. This is a huge deal. In physics, we have to understand that slopes of lines, variables, everything we do means something. This is why physics is awesome. Because in math class, yes, you calculate slope, and you do it 1,000 times. And you do rise over run, change in y over x. You do all that stuff that you did in Algebra 1. But in physics, it actually means something. So for us, the slope of a position versus time graph actually gives us the speed. That slope means something. Now, if we look here, how do you calculate slope? We calculate slope by doing what's called rise over run, or change in y over change in x. In our graph, the change in y is position. The change in x is time. So if we said that slope equals rise over run, which would be change in y over change in x. Hopefully you know what these delta signs mean. They mean change in. For our purposes, we would say that the speed, which is the slope, is going to be the change in position over the change in time. Now, I'm going to need to define something very specific here. The change in position, in our case, is going to be called x. The change in time is going to be called t. If you ever see a small t on my board, I guarantee you it's going to mean time. That's different in math class. In math class, you always solve for x or y, or maybe you had a cool math teacher that had you solve for a. Those are the variables that you solve for. They didn't mean anything most of the time. You could define x as anything. That's not true in physics. In physics, if you ever see a t on my board, it means time. If you ever see an x on my board, it means you've moved on the x direction. It's actually called a displacement or a distance. If you see a y on my board, it actually means you moved this way. Okay, you moved in the y direction. Z would technically be in and out. So x, y, and z are actually all positions on the x-axis, y-axis, and z-axis in the universe. Okay? T is always time. So for us, S, we're going to call it speed. What about when we moved forward or backwards? Right? What happens when we move towards the detector? What does that look like? Well, let's think about this. We would say that moving towards the detector, we started away from the detector. So I'm actually going to start up here at maybe 4 meters away. And then over time, we gradually got closer. So I might do something like this. This would be slow away, fast away, slow towards the detector. What would fast towards the origin look like? You're moving towards the car and you're moving fast. Well, we know that the slope is going to tell you how fast you're going. So in our case, starting here, you're going to go like this. This would be fast towards. What's the difference in those two slopes? You got a slope here moving away that's slow away. You got here going fast or slow towards. What's the difference in those? Well, it's the slope, isn't it? They have completely different slopes. So technically, the slope doesn't just tell us the speed or how fast we're going. The slope also tells us the direction that we're going. And direction is very important. Okay, so what we're going to do in physics is we're actually going to be describing the world around us. And the first unit we're going to look at is we're going to look at motion. How do things move? Are they moving fast? Are they moving slow? Are they accelerating? Are they falling? Are they going up? All of these things are going to be what we're going to focus on first. We describe motion, or actually we describe the world around us in 3 different ways. The first way is with words. We can say that I'm moving fast, I'm moving slow, I'm moving towards, I'm moving away, I'm moving up, I'm moving down, I'm accelerating, I'm falling through the air. These are words that we would use. Okay? The second way in which we describe the world around us is in terms of a graph. So we've already looked at one type of graph. This graph is position, meters, time, seconds. And if we had motion that looks like this, you might be able to say that it's moving away from the origin. You would say that it's moving away from the origin at a constant speed because the slope of this graph is constant. You might even say it's going slow, although it's kind of hard to tell because I didn't give you any numbers. But that's okay, we'll just look quantitative or qualitatively. The third way in which we describe motion is in terms of math. We've actually already looked at our first equation. We said that the slope of this line is rise over run. And we said that the slope gives us the speed of the car. And the speed of the car is how fast that it's moving. Our equation for speed is going to be change in distance over change in time. This is something you probably learned in 4th grade. Speed is distance over time. Another way to say this is that the rate times the time gives us a speed. All of these things are different ways to say this one equation. You look at how far you went and how much time it took you to do that, that gives you the speed. However, physicists don't really look at speed very often because this graph gives us more information than that. We want to be more specific than that. What other piece of information does this graph give us that isn't included in my equation? Well, what if the motion looked like this? This motion might have the exact same speed. It might be going 2 meters per second. This one here is going 2 meters per second away from the origin. This one here is going 2 meters per second towards the origin. But I think you and I would both agree they're completely different motions. If you're going one direction or you're going the other direction, that's a pretty big deal. And this graph gives us direction. Direction in physics is super important. This graph actually doesn't give us the speed, it gives us the speed and the direction. In physics, we call that velocity. The velocity is the speed and direction. Direction is key in physics. Let's talk a little bit more about that. So let me see if I can explain how vectors actually work and why they're so important. So in the situation here, I got my boy Anakin. He's traveling through Hoth. He's on vacation. Maybe he's looking for Padme. I don't know. But he gets stuck in a snowbank. So here's his car stuck in a snowbank. So Anakin comes out of this thing. He's sitting here going, oh my gosh, what should I do? So he comes to the back of his car. He pushes on the car. And he's pushing with all the force that he can. Now, let's say that Anakin can have 1,000 newtons of force pushing in that direction. But you know what? Not a strong guy. Can't get his car out of the snowbank. But along comes Obi-Wan. Oh, Anakin, what's your problem? Sorry, Master, I got stuck in a snowbank. Well, let me help you. So now Obi-Wan comes over, and he is also going to push on the car in the same direction. Now, Anakin can push with 1,000 newtons in that direction. Obi-Wan can push with 1,000 newtons in that direction. And so how many newtons do we have pushing on the car? Well, we have 2,000 newtons, right? Well, they're still not getting the car unstuck. So they wait a little while. They're waiting for some tauntauns to show up. And Anakin says, have patience, R2 will be along in a moment. But that just doesn't seem to happen. So then along comes Darth Maul. Now, Darth Maul looks at the situation and says, oh my, these guys aren't getting out of here. And Obi-Wan says, hey, can you help us get out of this snowbank? And Darth Maul says, no, I'm an evil Sith. But Obi-Wan says, do it or I'll cut you in half. And Darth Maul says, okay. So Darth Maul is going to help them get the car out of the snowbank. So Obi-Wan's over here pushing with 1,000 newtons. Anakin's pushing over here with 1,000 newtons. Darth Maul, however, evil Lord of the Sith, starts pushing on the car this direction with 1,000 newtons. So now we have 2,000 newtons pushing this direction, 1,000 newtons pushing that direction. What's the total force on the car? Well, Darth Maul is actually canceling out somebody on the other side. So the total force on this car is going to be 1,000 newtons, and the car is not going to be moved out of the snowbank. So Obi-Wan says, hey, wait a minute. You're not supposed to be pushing on that side of the car. That's not helping at all. And Darth Maul says, well, I don't really want to help you. I'm an evil Lord of the Sith. And these guys are like, yeah, it's 2 against 1, and I already cut you in half once. Why don't you come over here? So Darth Maul comes over here and starts to push on this side of the car with the Jedi Knights. So now we have the same number of newtons, the same amount of newtons pushing on this car, but they're all pushing in the same direction. So we have 3,000 newtons pushing in one direction. And of course, then the car comes out of the snowbank. Now think about that situation. We had the same force, right? The only thing I changed in that situation was the direction that Darth Maul pushed. When he was pushing this way, the answer was 1,000. When he was pushing this way, the answer was 3,000. So you can see that we get two completely different answers, and the only thing I changed was the direction. Direction is so important in physics. Most of the variables that we have are actually vectors for this reason. In fact, most of our variables, most of the things that we're going to look at involve direction. We call these vectors. A vector is any measurement that requires both a magnitude or a size and a direction. So this is magnitude and direction. Direction is key in these. Velocity is a vector. Speed is not. Speed just talks about how fast you're going. You have a speedometer in your car, a speedometer, which tells you how fast you're going. I'm going 55 miles an hour. Does it tell you what direction you're going? No, it just tells you how fast you're going. That's speed. If you also look in your mirror and you got one like north, south, east, west compass up there, and so you do know the direction, now you have velocity, speed, and direction. So magnitude is the size of the vector, and then direction tells you what direction you're going. This is some really intense vocabulary here. Because as a physicist, I'm going to start using some words, and I'm going to start using them in sentences, and I would expect you to understand what I'm talking about. Let me give you an example. What if I said, speed is the magnitude of the velocity vector? Oh, wow, that's a big statement. Speed is the magnitude of the velocity vector. Velocity is a vector. It requires magnitude and direction. What's the magnitude? If I'm going, my velocity vector, velocity is 40 meters per second due south. That would be a vector, right? So 40 meters per second is my speed. When I add due south to it, now I have velocity, v. If you ever see a v on my board, a lowercase v, it means velocity. Our equation for velocity has to not only include the distance that it goes, and sort of we can get the speed, it also has to include the direction that we go. And so for that, we need another vector. We need something that has a direction in it. And for that, we use what's called displacement. Displacement is distance and direction. So example, displacement is going to be, our variable for this is going to be x. Or it could be y or z. These are our displacement vectors. If you are on a road, and you're standing right here, and you move over here, you just displaced yourself. You have a change in x. You moved across from here to there. That's a displacement. Because here is our origin. That's where we started. But what if you then move back here? So now you also moved to here. Your total displacement is back here. It's negative. It's behind where you started. If you kind of define this as this is being x equals positive, and behind the origin is x is negative, you can have a negative displacement. That's kind of weird. You can go negative 2 meters. How do you go negative 2 meters? Well, to go positive 2 meters, I might walk over here. Moving in this direction would be a positive displacement. Moving in this direction is a negative displacement. Based on how I set up my Cartesian plane, right? Which is kind of an imaginary thing you can set up however you want. So we could say that you have a positive x. We could say that you have a negative x. That's displacement. Displacement is kind of a funny word. I think of it like this. I'm standing here in this place. I moved over here. Now I'm in this place. That is a change in position. I am in a new place. I've displaced myself. Okay? That's different than if I and start over here and move over here. Now I've displaced myself negatively. I came over here. So you can have a positive and a negative displacement. Typically, if we move towards the right, this way, we call that a positive displacement. Typically, if we move towards the left, we call that a negative displacement. If we move up, we call that a positive displacement. And if we move down, that would be a negative displacement in terms of the y direction. So our equation for velocity, let's get back to that. Our equation for velocity is going to equal not our distance over time, because we also have to include direction. It's going to be our displacement over time. It's going to be change in x over change in t. The change in x is your displacement along the x-axis. The change in t is the amount of time that it takes. If you look at the units on these, so velocity is going to be, change in x is typically for us, we're going to use meters. So this is going to be meters per second. Now technically you can do miles per hour. You can do kilometers per hour. You can do centimeters per millisecond. You can do whatever you want. But the standard unit in physics is meters and seconds. So if you have a velocity, it's going to be measured in meters per second. But you also kind of need to know the direction. If I have a velocity is 2 meters per second, maybe I'm going like this, at 2 meters every second. That's the velocity. I moved in the positive direction, 2 meters every second. What if I had a velocity of negative 2 meters per second? What does that mean? Well, that means I'm moving this way at 2 meters every second. The negative sign tells you the direction. It's positive if I'm moving this way, negative if I'm moving this way. Which we know that from the slope, right? If we looked at those graphs, if you had a positive slope, position versus time, if you had a positive slope, that's going to be moving away. If you had a negative slope, that's going to be moving towards. So in order to calculate this, you can do this a number of ways. You can actually sketch out the graph and calculate the slope of it, or you can just use this equation right here, our first kinematic equation, change in x over change in t. Okay, we essentially have one equation so far. Distance equals rate times time, or velocity is the displacement divided by time, or the change in position divided by time. One equation with 3 variables, yet we have all kinds of different things that we need to define in physics. Remember, variables in physics are very important. They are defined as specific things. If you ever see an X on my board, it's going to mean displacement. And it's not only just going to mean displacement, it's going to mean displacement in the X direction, going this way back and forth. If you see a Y on my board, if I ever see a Y on a sheet of paper as a variable for you, I'm going to expect that it means going up and down in terms of displacement. Distance is D. Distance is the scalar part of displacement. D is the distance is the magnitude of the displacement vector. That's how far you went. It doesn't tell you the direction. Okay, I know that was a lot of vocabulary, but hopefully we're getting into some of those vocabulary words. T is time, typically measured in seconds, but you could measure it in anything. Milliseconds, microseconds, hours, whatever. V. A regular V actually means instantaneous velocity. This is how fast you're going at the moment. If you look down your speedometer, that's how fast you're going. And with the direction maybe from your compass, you can get your velocity instantaneously. V with a bar across it, if you ever see a bar across one of these variables, it means average. You're looking at it over an amount of time. For instance, if a car is speeding up, then it has a instantaneous velocity. Maybe it's going 2 meters per second, then 3, and then 4. But overall, on average, you look at how far it went and how long it took to get there, and that's your average velocity. So going back to this idea of traveling to Iowa City, my average velocity was 60 miles per hour if I'm going 60 miles in 1 hour. But instantaneously, my velocity was whatever it said kind of on my speedometer. And finally, this idea of initial velocity. The initial velocity we talk about, we use a variable. If you ever see a little tiny zero next to a variable, that means initial. Technically, I think it's V naught. They call it naught. I don't know if it's an English thing, but V naught is initial velocity. So maybe you started at rest, so your initial velocity would be 0. Maybe you were moving and then you slowed down, then your initial velocity would be whatever you started with. So you can see that just doing distance equals rate times time, there are a lot of variables to keep track of. Be very cautious about which variable you're using in your equations and in your solving of problems. So today's task, we are actually going to take this to another level. We've been talking about position versus time graphs. Position versus time graphs have position on the y-axis in meters and time in seconds on the x-axis. Now, when we looked at these, you should be able to figure out how things are moving or be able to draw a position versus time graph based on how something is already moving. For instance, if it's moving like this versus if it's moving like this versus if it's moving like this or if it's moving like this. We've kind of dealt with position versus time. This is where you should be right now. Today, we're actually going to look at a different type of graph. We are going to look at what's called a velocity versus time graph. How is the velocity changing? What's happening with the velocity or speed and direction of the object or of the car? So that's going to look like this. Velocity is in meters per second and time is in seconds. I actually have my zero, my origin right here, because velocity in these graphs can either be positive if it's moving away from the origin or negative if it's moving towards the origin, because velocity is a vector. So today you're going to actually use the exact same data that you used before. You know the experiment I did. I pushed the car towards slowly, I pushed the car towards faster, I pushed the car away slowly, I pushed the car away faster. So what does Tesla look like? What does the Tesla Vision look like in terms of the velocity graphs? If you open up that data in Logger Pro using your Chromebook, you should be able to pull up the velocity graphs for each of those runs. I want you to look at those and make some claims about how the graph can tell us the motion. What does a velocity versus time graph look like if it's moving slowly away, or quicker away, or slowly towards, or quickly towards? Make a claim, but be sure that you base that claim on evidence, and the evidence should come from that data. The evidence should come from the graphs. So you're going to want to paste those graphs so you can refer to them when making your claim. Okay? After that, you're going to see that there's a bunch of talk about what's called acceleration. Acceleration is actually a pretty complicated topic. We're going to get into that next time. But I want you to read through that and try to figure out what's going on with acceleration. Can you answer those questions at the bottom of the lab based on the reading that you have available to you? If you have any questions, be sure to let me know. We will be talking about this in class or on discussion boards. But be sure that we are in contact if you're having any troubles. I know this is going to start to get a little bit more complicated, and hopefully we can keep moving forward. So good luck. Let me know if you need anything, and I will see you soon.